Hello, Calculus 1 students. Today, we are discussing linear first-order differential equations, how to solve them. So far, we have seen separable differential equations, autonomous differential equations, where we looked qualitatively at solutions, and then we also verified solutions in other differential equations. There's so much more to the story of differential equations. In fact, this is our last lesson in our Calculus 1 course. But I encourage all of you to take a full course in differential equations. Very beautiful, and you can learn more things. But for today, our definition right here, a linear first-order differential equation has the following form. We have dy dx plus some function of x times y equals another function of x. So you notice there's no y squared, there's no y times dy dx. It's just dy dx plus y times some function of x, and then equals another function of x. Well, let's begin with an example. And initially, I'm going to say, let's multiply by x squared and see what happens. And it seems like kind of magic. Really, it kind of is. But we will then discuss what's happening and how we could solve these in general. So let's do exactly what I suggest. Let's multiply this differential equation, dy dx plus 2 over xy equals 4x plus 1. Multiply the whole thing through by x squared. We get x squared dy dx plus, well, this will be 2x y, and then multiply the right-hand side by x squared. I get 4x cubed plus x squared. Okay, if you stare at this, we see something here. What I see is product rule. So if you don't see that, let me write it and then we can verify. The left-hand side is x squared y prime. And I'll just recopy the right-hand side. 4x cubed plus x squared. Now, why is this my left-hand side? Okay, what will we do when we take product rule? We would have first derivative of the second. Remember, y is a function of x. And then plus, here's the second, derivative of the first. It's exactly the product rule here. So I have x squared y prime equals 4x cubed plus x squared. Well, we could just integrate both sides. So the left-hand side, I have x squared y. The right-hand side, I will have the integral of 4x cubed plus x squared dx, which each term is just power rule. I have x to the fourth. I have plus x cubed over 3 plus c. Now, how do I solve for y in terms of x? You notice I can just divide by x squared. So I get that y is, okay, divide everything by x squared. We get x squared plus x over 3 plus c over x squared. And this would be my final answer. I have explicitly solved for y as a function of x, and this is the general solution. My question, how do we solve this general first-order linear differential equation? And we use what's called an integrating factor. So if we back up, this magic multiply by x squared, this was our integrating factor. In general, the integrating factor I of x we define to be e to the integral p of x dx. However, let me make an important note here. Really, we just need one antiderivative. One antiderivative of p of x. And so, at least when we write down the integrating factor, we don't have to worry about the plus c. I'll make this remark again later. So the other thing that I'll point out before I get into product rule, which is coming very soon, is what do you notice about the derivative of I of x? This integrating factor, well, it is chain rule. We take derivative of the outside, evaluate it at the inside, and then times derivative of the inside function. When you differentiate an antiderivative of p of x, we just get p of x. Okay, so we could also write this as I of x times p of x. Very nice. I'm going to use this shortly. So what do we do here? Well, just like when I multiply through by x squared, we are going to multiply through my differential equation by I of x. And what do I get? Well, on the left-hand side, I have I of x dy dx plus I of x p of x y, and this equals I of x q of x. Okay, so the left-hand side, just like we saw in the example on the last page, the left-hand side really is the product rule. Let's write it. This will be I of x times y prime. As we saw in the last example, here is first derivative of the second plus the second times derivative of the first. That's what we justified at the beginning. The derivative of the integrating factor is I of x times p of x. Now, the next step is we integrate both sides. And then finally, we solve for y. Okay, well, this is very abstract looking. So let's go back and do an example to help us understand these steps. Here is a wonderful sort of first example using an integrating factor where we calculate the I of x. We see this is handed to us already in the form that we need. And so we can just immediately write down I of x. I of x will be e to the integral. Well, the p of x is minus 5. So we have minus 5 dx. You notice this is just e to the minus 5x. As I mentioned, I'm looking for one antiderivative of minus 5, and certainly minus 5x works. Okay, so now let's multiply through the whole differential equation by e to the minus 5x. We have e to the minus 5x dy dx minus 5 e to the minus 5x y is 7 e to the minus 5x. Well, here's our product rule we're staring at. You see, the left-hand side is e to the minus 5x, and then we have y prime. You can always check. You see, we have first derivative of the second, and then plus the second. This part is derivative of the first. You think about the chain rule. So we integrate both sides. The left-hand side becomes e to the minus 5xy, and the right-hand side, when you integrate, we have a negative 7 over 5 e to the minus 5x plus c. Final step, solve for y. Here, this amounts to multiplying this equation through by e to the 5x. And so we have y equals minus 7 over 5 plus c e to the 5x. Really, I've used properties of exponents here, that e to the minus 5x times e to the 5x. This is 1. Okay, so here's our answer. Let's see. Maybe for this one, let's verify. We know if you have some differential equation and you think you have a solution, you can always check. So let's do that. Maybe I'll move this over. This is not required. We have solved the problem, but I have space on the page. So let's check. We can check. Let's take our y and calculate dy dx. Well, the derivative of the constant is 0, so we get c e, the 5x, times the derivative of the inside function. Well, the differential equation says dy dx minus 5y, and this should equal 7. So dy dx minus 5y, this is 5ce to the 5x minus 5. And then y itself was minus 7 over 5 plus c e to the 5x. What do we get? Well, you notice that we have 5c e to the 5x minus 5c e to the 5x. And then we have minus 7/5 times minus 5, which is 7. Okay, but this is actually a nice activity. We have verified that the solution we found works. Nice sanity check here. Next example, find the general solution of this differential equation. Xy prime equals 3y plus x squared. Now, you notice it's not yet of this form. And so the first step will be to write it of this form. I'm going to be dividing by x here. So maybe I will just make my life a little bit more simple and require x to be positive. Okay, so now let us write it of this form. We will have dy dx. We would have a minus 3 over x, y, and then this will equal x. What I did is I just moved this term over here and then divided everything by x. Fantastic. Now we're ready to write down our integrating factor. I of x, this will be e to the integral of minus 3 over x dx. Really, I just need one antiderivative here, and I can use minus 3 ln x. Well, let's simplify this more. So there's a few things I can do here. Maybe I'll do this. We can write this as e to the ln x raised to the minus 3, right? Power to a power, we multiply. E to the ln x is x. And so I just get x to the minus 3. You can certainly write that as 1 over x cubed. It's fine, but I'm just going to leave it like this. So let's multiply through. We have x to the minus 3 dy dx. This one will be minus 3 x to the minus 4 y. And then we have this equals x to the minus 2. The main reason I kept these negative powers is because, well, it's easier for me to use the power rule. So this side, we can definitely see product rule. We have x to the minus 3 y prime, okay? First derivative of the second plus the second derivative of the first, and then this just equals x to the minus 2. So let's integrate. We have x to the minus 3y equals, we add a power and divide by the higher power plus c. Now my final step, we solve for y. So we get y equals, multiply through by x cubed. I'm going to have minus x squared plus c x cubed. Here's my final answer. Now, maybe I can make some of this smaller. I'll make my integrating factor another color, and then I can move some of this up. So my remark about this question is, You see, to make my life easier working with the differential equation, I just assumed x was positive. In particular, I divided by x, and then, well, to write 3 ln x instead of ln absolute value of x, you might want to say that x is positive. But then in the end, I came to a solution. This y is defined for all x. And it can be a nice check to see that, in fact, this y satisfies the differential equation really for every x. So let's just do that. It's a nice way to end this example. If you take x, y prime, we have x times, well, y prime is minus 2x plus 3cx squared. We get minus 2x squared plus 3cx cubed. Okay, this is the left-hand side of my differential equation. The right-hand side, 3y plus x squared, 3y plus x squared equals 3 minus x squared plus cx cubed plus x squared. And we have, okay, we have minus 3x squared plus x squared, which is minus 2x squared. And then we have 3cx cubed. And you notice these are equal. So, in fact, my solution, well, it works in general. Okay, next example. Here we have an initial value problem, so my final answer will not have a constant of integration in it. All we need to do here is we can quickly rewrite this as y prime minus y equals 2e to the x. So my integrating factor, we have e to the integral of minus 1 dx. We can use minus x as an antiderivative for minus 1. Okay, great. So we multiply through by e to the minus x. We have e to the minus x y prime minus e to the minus x y. Here, when I multiply through by e to the minus x, I just get 2. The left-hand side, e to the minus x y, quantity prime, product rule, and you can check first derivative of the second plus the second. That's the derivative of the first using the chain rule. And then this equals 2. So my general solution, which I'm not finished yet, my general solution, well, I would have e to the minus x, y will be 2x plus c, and then we multiply through. So I get y is 2x, e to the x plus c, e to the x. Okay, but I'm not done yet. As I was saying, I need to use my initial conditions. And so evaluate at 0. Well, this part is 0. We get c, e to the 0. E to the 0 is 1, so we just get c. On the other hand, let me move this over. We are told y of 0 is 3. And so my constant is 3. Now I have my final answer, my particular solution. Y is 2x e to the x plus 3 e to the x. This satisfies the differential equation, and y of 0 is 3. Wonderful. I mentioned this earlier, but it's worth writing down because this is very important regarding the constant of integration. For the integrating factor, well, we need any antiderivative. Works. And so what this means is you do not need plus c. Okay, any antiderivative of p of x works. It's really to establish this product rule on the left-hand side. But when you go to integrate, once you multiply the right-hand side, the q of x, here, this q of x by the integrating factor, you see you're going to be integrating I of x, q of x. The c is fundamental. Okay, so we absolutely must have the plus c. We must have a constant of integration. And we can really see why, or one reason why, on this example we just did. Because, well, if you didn't put this constant here, we would not be able to solve. All we would have would be this part. And then if you try to evaluate y of 0, you'll get 0. So you're losing part of the solution. In general, say we back up to 1 here, you would lose this whole part of the solution if you don't have your constant integration. So this is very important on when you're integrating I of x times q of x, that you include the constant of integration. All right, let's do one more like this, and then I'll make a remark about a shortcut that you can use if you'd like. So this differential equation is almost of the right form. What I need to do, I'll write it here, y prime, we have minus 2x, y, and this will equal, I just need to subtract this 6x cubed e to the x squared. So now I have it exactly of this form here that we're wanting when we look at a first order linear differential equation. Okay, so my integrating factor, I of x, we take e to the integral of minus 2x dx. Really, we need one antiderivative, which would be negative x squared. So this is e to the negative x squared. We have e to the negative x squared y prime minus 2x e to the minus x squared y. And then this will equal, you see it's minus 6x cubed. Because when you take e to the minus x squared, multiply by e to the x squared, we have 1. Okay, so the left-hand side, at this point, we should not be surprised. Product rule. We have e to the minus x squared. Y, quantity prime, is minus 6x cubed. Because if we stare at this, we have first derivative of the second plus the second. And then here, this is derivative of the first, chain rule. Okay, so let's integrate. We have e to the minus x squared y equals, well, this is power rule. It will be minus 6x to the 4th over 4, or you could write it as minus 3 over 2 x to the 4th. Don't forget the plus c in this step, so plus c. Finally, we solve for y, which in this case, we multiply through by e to the x squared. So y equals minus 3 over 2 x to the 4th e to the x squared plus c e to the x squared. General solution. We have a c in our answer. Fantastic. Now, this is a remark because we can sort of see a pattern after we do enough of these. So what happens when we want to solve a first order linear differential equation? Well, calculating the integrating factor is fundamental. In fact, step 0 is to write it of this form where you see the p of x and you see the q of x. Then we find one antiderivative of p of x, and we take e to the, that's our integrating factor. So the left-hand side will always be, oh, in fact, I can back up to the very beginning. It will always be I of x, y prime, and then equals I of x, q of x. So this part you're going to integrate with the constant of integration. And then divide by I of x to solve for y. So let's go back and look at that formula again. It's here. If you want to remember it like this, you can. We've certainly practiced the product rule part of it several times. But if you want to remember it like this, perfectly fine. The only thing is take care. This integral right here absolutely must have the plus c. Otherwise, as we've discussed, you're losing, well, a lot of the solution. Okay, so let's do one more where maybe I'll do this shortcut. Okay. We have an initial value problem. Wonderful. So my initial step, we have a natural log. X is only positive in this problem. So let's divide by x squared. We will have dy dx plus 1 over x y, and this equals ln x over x squared. So here is my differential equation. Okay, now here is my p of x. Let's paste it one more time. Okay, we have to do that so we can spot the p of x, and I see it. P of x is 1 over x. So my integrating factor, I of x, this will be e to the integral 1 over x dx, which I just need one antiderivative. In particular, I see a log here, so x is always positive. We can take e to the ln x. This is x. Then my y will be 1 over this integrating factor. Maybe I'll do it in 2 steps. Times the integral I of x, q of x, dx. So here, my integrating factor is x. So 1 over the integrating factor is 1 over x. But my integral, well, when I multiply this by x, you see I get ln x over x. How am I going to integrate this function? Substitution. Because here, I see an inside function. Sort of, I have the natural log and multiple of its derivative in my integrand. So for this integral, u is ln x du 1 over x dx. Now I have exactly du in my integral. So my integral becomes, maybe I will do this on the side. The integral, natural log x over x dx. This is an integral, well, it's u du. So I get u squared over 2 plus c. Go back to x. So this will be natural log x squared over 2 plus c. Okay, here's maybe my little box of side work. At this point, I have found this indefinite integral using substitution. And so let's write our solution for y. Y is 1 over x, which was 1 over the integrating factor, times this, which is ln x squared over 2 plus c. So I think I could distribute this 1 over x, and I think I will in my final answer. However, we have to remember here, we are looking for a particular solution. We are looking for the solution in which y of 1 equals 2. So let's evaluate y of 1. Well, we have 1 over 1, okay? The natural log of 1 is 0. So we just have 1 times c. And this is supposed to equal 2. We can see here my constant is 2. Now I can write my final answer. We have y. This will be ln x squared divided by 2x plus 2 over x. This is my particular solution. I like this question because we had to solve an initial value problem. We also had integration by substitution. So it was quite fun. Well, thank you so much, students. This is the end of our first order linear differential equations video.